Today, we're going to discuss autonomous differential equations in population dynamics. Let's review some concepts. Recall that a first-order differential equation is in the form y prime equals g of ty for some function g. We'll say that such a differential equation is an autonomous equation if this function g is a function of y alone. That is, we'll write g of 2y equals f of y for some function f. We've already seen some examples of autonomous equations. First, let's say perhaps if we have a mass m falling under the influences of gravity and air resistance. If v denotes the velocity at a time t of such a mass, then we found that dv dt, the acceleration, is equal to negative g minus gamma over m times v. Here gamma is going to be our constant proportionality for our drag coefficient. We see that the right-hand side here, negative g minus gamma over m times v, is just a function of the velocity v alone. Therefore, it is an autonomous equation. As another example, let's say that p denotes the size of a population at time t. We've seen before that there are constants r and k, so that dp dt equals r times p times 1 minus p over k. Here, r would look like our growth rate. You'll notice that the right-hand side of our equation, r times p times 1 minus p over k, is just a function of the population size p alone. It's not a function of time. This fits into a slightly more general family of equations that we'll call Bernoulli equations, which we can write in the form dy dt equals to some power of y, namely y to the n. Well, here, if either n equals 0 or n equals 1, this would just be a linear differential equation, and we've already seen how to deal with these. So more generally, we can consider dy dt equals y to the n, where n does not equal 0 or 1. These are also examples of autonomous equations. We can try to determine the behavior of solutions to such equations as t increases without bound. In particular, let's say that y of t is a solution to such an autonomous equation. Then, as t increases without bound, this function y will tend to a constant, which we'll denote by y sub l. We'll call this an equilibrium solution. You'll notice that if we have an autonomous equation, then g of ty equals f of y, which of course is independent of time, and therefore f of l has to be 0. Remember that y sub l should be a constant. This means that y sub l is the root of some equation, f of y equals 0, so we'll call y sub l a critical point for the function f of y. We're going to focus on this in some detail today. Let's discuss an application of autonomous equations by considering the concept of population growth. We'll start with the definition. Say that we have a population that has size p of t at some time t, where we have some initial population size p0. We're going to make the assumption that the rate of change of size is proportional to both the size of the population and the difference of the size from some maximal sustainable size k. Here, think of this as we may have some population, and if the population gets too big, then we've taxed our resources too much, and people may decide that they want to leave that city. The equation that we find is dp dt equals r times p times 1 minus p over k. Here, r is the rate of growth, and k is our saturation level, or you can say r environmental carrying capacity. We'll call this differential equation the logistic equation. Fortunately, we can solve this equation because it is a separable equation. We've found before that the unique solution to this initial value problem is p of t equals p0 times k divided by p0 plus k minus p0 times e to the negative rt. Remember here that p0 is the value of our function when t equals 0. Moreover, as time increases without bound, we can see that the solution p of t tends to one of two values. That is, we have two different equilibrium solutions. Either 1, p sub l equals 0, or 2, p sub l equals k. We can find these equilibrium solutions by taking a look at our autonomous equation, writing this as dp dt equals f of p, and realizing that the right-hand side is f of p equals r times p times 1 minus p over k. We'll find the equilibrium solutions by setting f of p equals to 0 and then solving for p, namely p equals 0 or p equals k. Sometimes it'll be more useful to consider these so-called normalized functions. Instead of considering the absolute population size p, we may consider the ratio of the population size to its maximum carrying capacity. We'll think of y of t in this case now as more like a ratio or perhaps a percentage. So intuitively, y of t really should be between 0 and 1. We're not going to focus on this too much in today's lecture, but this is saying that sometimes it's more helpful to focus with this normalized function. Now, more generally, let's go back to an autonomous equation, y prime equals f of y. We've already discussed how we can perhaps find equilibrium solutions by setting f of y equal to 0. But let's consider this in a bit more detail today. Remember that for any function, we have the concept of a Taylor series expansion around some point y equals y sub l. In this case, we'll write out the Taylor series expansion by saying f of y equals a constant, f of y sub l, plus the first order term, f prime of y of l times y minus y sub l, plus higher order terms. By only looking at the first order term and remembering that we are looking at an expansion around an equilibrium solution, we can approximate f of y as a constant a times y minus y sub l. Remember that the constant here is just the derivative evaluated at our equilibrium solution. Simply put, we can summarize as follows. Say that we have an autonomous equation and we assume that y minus y sub l is small. That is, we're very near the equilibrium solution. Then we have an approximate differential equation, dy dt equals approximately a times y minus l. Again, a here is a constant. We can solve this first order equation to find approximately y sub l equals y of t equals y sub l plus a constant times e to the at. This allows us to consider two possibilities. If this constant a is negative, then e to the at approaches 0 as t increases without bound. This means that y sub t approaches y sub l over time. On the other hand, if this constant a is positive, then e to the at gets larger and larger and larger. This means that y of t grows away from y sub l as t increases without bound. So in the one case, when a is negative, it approaches y sub l, but in the second case, where a is positive, it grows away from it. This then motivates two definitions. Again, say that we have an autonomous equation, y prime equals f of y, and say that y sub l is an equilibrium solution. That is, f evaluated y sub l equals 0. We'll say that y sub l is a stable equilibrium solution if the derivative f prime of y sub l is negative. If the derivative is positive, we'll say that y sub l is an unstable equilibrium solution. Notice that we do not give a definition if f prime of y sub l equals 0, only if it's either negative or positive. Let's focus on an example. Let's consider a function f of y equals a constant r times y times 1 minus y. We can consider the derivative here, f prime of y, to be r times 1 minus 2y. Assuming r is positive, we can now plot out our function and realize that as long as y is less than 1/2, then f prime of y is positive, and therefore we have an increasing function. On the other hand, when y is greater than 1/2, then f prime of y is negative, and therefore we have a decreasing function. We can now consider in more detail what happens when either the derivative is positive, an increasing function, or the derivative is negative, a decreasing function. Well, first, by setting f of y equal to 0, we can find two equilibrium solutions, namely y sub l equals 0 and y sub l equals 1. When y sub l equals 0, We then see that the derivative, f prime at 0, is positive, and therefore we have an unstable equilibrium solution. On the other hand, when y sub l equals 1, we see that f prime of y sub l is negative, and therefore we have a stable equilibrium solution. So by just looking to see if our function f of y is either growing or decreasing, we can actually determine when we have an either unstable or a stable equilibrium solution. Let's go back to the concept of population dynamics. I want to write down a differential equation that's a little bit different from what we've been studying up to this point. Let's consider an autonomous equation, f prime equals f of y, subject to the condition y of 0 equals y naught, in terms of the function f of y equals negative r times y times 1 minus y over t. Up to this point, we've been considering positive r times y times 1 minus y over t. Let's consider a negative r now, where here r and t are positive numbers. We can work through to find our solution, just like before. Nothing really is going to change. But let's ask, what happens now as time increases without bound? Well, e to the rt should grow larger and larger as t grows, so we expect the solution y of t to grow to 0. But I want to ask the question, is this really the case that our solutions all tend to 0? Let's write out the answer as a proposition. First, we notice that our function f of y has two critical points. We can set f of y is equal to 0, and we find that either y equals 0 or y equals t. There are two critical points. Now let's take a look at our function f of y, just like before, and let's try to ask what happens if our initial value, y sub 0, is in a certain region. If y sub 0 is between 0 and t, we see that f of y is negative. Since f of y, of course, is the derivative of y prime, we see that a solution, y of t, must be a decreasing function. That is, if initially y of 0 is less than t, then our function, our solution, must be decreasing. On the other hand, if y0, our initial value, is greater than t, then f of y is positive, and because y prime equals f of y, we see that the derivative has to be positive, and therefore our solution, y of t, must be an increasing function. So this means that whenever our initial position y0 is less than the threshold t, then all of our solutions must tend to 0. Remember, y of t is a decreasing function. That is, the limit as t increases without bound of y of t equals 0 whenever y is less than t. We're going to call this parameter t our threshold for this reason. That is, if anything is less than t, then everything seems to die out to 0. Now, if you don't like this discussion, we can do the same type of discussion, but now considering a direction field. Here, we have on our horizontal axis the time t, and our vertical axis we have our value y. You have two solid black lines corresponding to the two critical values, y sub l equals 0 and y sub l equals t. You'll notice that as long as y is between 0 and t, we have this dotted vertical arrow that says everything must go down. Our direction field tells us that all of our solutions, y of t, must tend to 0. On the other hand, whenever we have an initial value y sub 0 is greater than t, you can see we have a vertical dotted arrow that moves up. This says that all of our solutions must continue to increase and increase and increase. So the direction field here does tell us if y sub 0 is less than t, then all of our solutions tend to y sub l equals 0. However, if y sub 0 is greater than t, you can see that all of our solutions must continue to increase. Let's put all of this together as a statement and a proposition. Say that we have a population size p at time t. We're going to keep track of two properties. Number one, there's some environmental carrying capacity k, so that if our population is greater than k, then the population must decrease in size because the population has exceeded its resources. Second, we'll keep track of a threshold t. That is, if our population is less than t, then we expect our population to go extinct. That is, there really aren't enough people around to help continue to grow the city. We're going to assume that our rate of change of the size of the population is proportional to three factors. Number one, the size p. Number two, the difference between the carrying capacity k and the size p. And number three, the difference from the size p to the threshold t. Putting all of this together, we actually find an initial value problem. That is, dp dt equals negative r times p times 1 minus p over k times 1 minus p over t, where of course p of 0 is our initial size, p naught. Remember here that k is the environmental carrying capacity. It says that if the population gets too big, there really are too many people and the population will start to die out a little bit. On the other hand, the threshold t tells us that if there aren't enough people in the population, then this population will go extinct. So somehow these two parameters, the environmental carrying capacity k and the threshold t, should do a much better job of modeling what really happens in real life. This equation here we will call the logistic equation with threshold. Now, going back to this equation, we can try to ask the question, what do we know about the behavior of the population as time increases without bound? So let's write our autonomous equation as dp dt equals f of p, where the f of p is what you see here on the screen. We can plot out this function and take a look at our three critical values, namely p equals 0, p equals t, and p equals k. Those are the three blue dots you see here on your screen. Well, if our size p is not too big, then we'll see that as we move from left to right, we have a decreasing function. At some point, this function will turn around and it'll become increasing, but as p gets larger and larger, we'll find that this function is decreasing once again. You can figure out the vertical slashes here on the screen by taking the derivative of f and asking when is this equal to 0. We won't worry about doing that today. We'll simply remark by saying that this function f of p has three critical points, namely p is equal to 0, p is equal to t, and p is equal to k. Because our function is decreasing in the regions to the left and the right on your screen, we'll see that p equals 0 and p equals k are stable equilibrium points. On the other hand, in the middle of the screen, you'll see that our function is increasing, so we see that p equals t is an unstable equilibrium point. Here, kind of the idea for p is equal to t is that if we're just a little bit below having population size equals to the threshold, that is, p is slightly less than t, the entire population dies out to 0. But on the other hand, if p is just a little bit greater than t, if the population is slightly greater than the threshold, then everything will increase and increase up to the size of the maximum carrying capacity k. Those are two very different values, even though p is very near the value of t. Now, to get a better idea of how the limit as time increases without bound of our population depends on the initial value, we're going to consider the slope field. Let's think of it this way. If the population is between 0 and t, then our function f of p is negative, but this is the derivative f dp dt, so we expect our population to be a decreasing function. Again, the idea is that our population is below threshold, so expect the population to become extinct. Second, what if the population is between the threshold and the environmental carrying capacity? In this case, we can plot out that f of p is positive, that is, dp dt is positive, so we expect to find an increasing function. In this case, the population is below the carrying capacity, so we expect our population size to increase. Finally, if p is greater than k, we can work out that f of p is negative once again, so our population should be a decreasing function. Again, this makes sense because then the population will be above the carrying capacity of the population. We can place all of this into a direction field as you see here on your screen. Again, remember that the horizontal axis is time and the vertical axis is our population size. You can see here three distinct horizontal lines that correspond to p is equal to 0, p is equal to t, and p is equal to k. If our population size is between 0, and t, we can see that all of the lines seem to slope downwards down to p is equal to 0. On the other hand, as long as p is greater than t, we can see that all of our lines seem to converge together to p is equal to k. This is exactly what we expect. So finally, putting all of this in one place, as time increases without bound, our solution will tend to 0 whenever we're between 0 and t, and our solution will tend to k whenever p is greater than t. Thanks very much for watching.